All right, so yeah, I'm recording the session. Perfect. All right, so yeah, the mean value theorem. Let me first remind you the Rolle's theorem. Okay, so we discussed Rolle's theorem last time, and I think we had a couple of examples. So what does it say, the Rolle's theorem? It says the following: you have a continuous function on closed interval AB, so f of x. It's some continuous function on a closed interval AB, right? And with the f of a equals to f of b. Okay, so it's continuous and of course differentiable because we're gonna use the derivative, and f of x is also is differentiable. So when I say f of x differentiable, it means that the derivative of f of x exists. So it's differentiable on the open interval AB. Okay, so here I exclude a and b, such that f of a is equal to f of b, right? So the theorem says the following. Then they exist. So the conclusion of the theorem is the following. There exists a number c in the interval AB, and a number c. There exists c in the interval AB, such that f prime of c is equal to 0. And f prime of c is equal to 0. Right. So we said the idea is that you know, you have this function which is continuous on this differentiable on this interval AB, and we said the f of x would have, you know, a global, either a global maximum or a global minimum on this interval AB. And if you have a global maximum or a global minimum, then let's say at c, then f prime of c is equal to 0, right? So that's why we have this number c such that the derivative at c is equal to 0, because you know that there exists, you know, that f of x has either a global maximum or a global minimum on this interval AB. That's why such number c exists, right? Because you know there exists a global maximum or global minimum, right? Anyway, I think we had a couple of examples where you have to show that some equation has like at most two solutions, or you know, at most two solutions, or at most three solutions, etc. I'm gonna give you one more example, guys, because that would probably cover. So in the homework, if you check the homework number 9, the problem number 5 and 6. So in the problem 6, it says like show that the equation has at most two real roots or two real solutions. So we had a similar example last week, right? Now a similar example to the problem number 5. Problem number 5 says that the equation has exactly one solution, right? So I'm going to explain how to do this problem number 5 in the homework number 9. Okay, so I'm gonna do like a similar example to the problem number 5 in the homework. Okay, so this is an example. Okay, so I'm gonna give you an example. So we're gonna apply the theorem, right? So the goal, of course, is to apply the theorem. So I'm gonna give you an example. So this is similar to the problem number 5 in the homework. Problem number 5 in the homework 9. All right. Okay, so let's say we have the following problem. You have, let's say you have to show that let's say for let's see, show that the equation um, 2x minus 1 minus sine of x, okay, equal to 0, has exactly, so here we have to show that the equation has exactly one solution. Okay, so one solution or one root. Okay, so when I say a root means a solution. Okay, it's the same thing, solution or a root. Okay, one solution or exactly one root. Okay, on the interval 0 pi, let's say. Okay, so we have this equation, right? 2x minus 1 minus sine of x equal to 0. So you wanna prove that the equation has exactly one solution, right? So there are two steps to answer such a problem. Okay, so first step, you have to show that there exists at least one solution. So there are two steps. So first step, you have to show that the equation has at least one solution. So we have to prove. So we have to show that the equation has at least one solution. So when I say at least one solution, means it could be one. The equation could have like one solution or two solutions or three solutions, etc. Right? So it could have one solution or more than one solution, right? So when I say at least one solution, it means either one or more than one. Okay. Then the second step, you have to show that the equation has no more than one solution. No more than one solution. Okay. Again, guys, here the idea is, so we have this equation. You cannot really solve explicitly the equation, right? So you cannot find like the explicit value of the solution. So the idea is to try to use this Rolle's theorem or the intermediate value theorem to say, well, I know by the intermediate value theorem or by this Rolle's theorem that there exists at least one solution, but you don't know the exact value of the solution, right? Now, in this step 2, if you show that the equation has no more than one, so in step 1, you show that the equation has at least one solution. And then in the step 2, you show that the equation has no more than one. So if you have at least one solution and no more than one at the same time, then the conclusion is that the equation would have exactly one solution, right? So then the conclusion, so then we can conclude that the equation has exactly one solution. Okay, so then we can conclude, because of the step 1 and the step 2, we can conclude that the equation has exactly one solution. So so from step 1, I'm gonna just probably zoom out. All right, probably it's better if I zoom out. All right, so step one combined with the step two. So if you combine the step one and the step two, then you can conclude. So then we deduce. So we deduce that the equation has exactly one solution. Has exactly. So I'm going to explain how to prove the first step and also the second step. Exactly one solution. So again, guys, the idea is first you show that the equation has at least one solution, right? So it could be one or it could be more than one, right? And the step two, you show that the equation cannot have more than one. So if you show that the equation cannot have more than one, it means either no solution or one solution. So if you have at the same time one or more solutions or one or zero solution, then you can say actually your equation has exactly one solution. So we see why if we combine the first step and step two, then you can actually deduce what we want, that the equation has exactly one solution. Now, so is there any question about the steps first, guys? So you see why if you combine the step one and step two, then you can conclude that the equation has exactly one solution. All right, so how do we do the first step? Well, step one, to show that the equation has at least one solution, we're gonna use the intermediate value theorem. So for step one, we're gonna use the intermediate value theorem. Okay, so how does it work? Well, so I'm gonna define f of x, my function f of x, as so equal to this 2x to this equation 2x minus 1 minus sine of x, right? So let's say, so my f of x is 2x minus 1 minus sine of x. All right, so what does it say, this intermediate value theorem? Well, remember intermediate value theorem, if you have, let's say, so the idea is the following. So if you have a positive and a negative value of f of x, let's say this is, this is your f of x, right? So let's say for a here, for this f of a, this is f of a, all right? And this one here, this is, so this is a, this is b, all right? And then you have this is b, so this is f of b. So if f of a and f of b, they have opposite sign, so let's say f of a is negative, f of a is negative, and f of b is positive. So to go from negative to positive, right? So then you have to cross the x-axis, right? At some point. So at some point, let's say here C, right? You're gonna intersect the x-axis. So what does it mean for f of x to intersect the x-axis? It means that f of c would be 0, right? So then f of c would be 0. So again, C, that's where your graph intersect the x-axis, right? So then f of c is 0. So if f of c is 0, it means that c is a solution of your f of x equal to 0, right? So then c is a solution. Okay. So then c is a solution. Is a solution of f of x equal to 0. Okay, so all you need, guys, is some is a positive and a negative values of your function f. So then because your function is continuous, then you have to cross the x-axis. So you have to intersect the x-axis, and that will be a solution. But of course, you could intersect the x-axis at more than one point. So for example, like if you have a different situation where, let's say, again, this is A, this is B. And so each time you intersect the x-axis, that will be a solution, right? So let's say here's your f of A, this is f of B. So you could, for example, have something like this here, right? So in this case, you would have like more than one solution. You would have like 1, 2, 3, 4, 5 solutions of f of x equal to 0, right? Because each time you intersect the x-axis, there will be a solution of f of x equal to 0. So, but you're gonna cross the x-axis at least one time, right? Because if you go from negative to positive, you have to cross the x-axis at least one time. So that means that with this intermediate value theorem, you know that there exists at least one solution of f of x equal to 0. Of course, you could have more than one, right? Like here, we would have like 5 solutions, 5 times. So we're gonna cross the x-axis at 5 different places, right? So there'll be like 5 different solutions of f of x equal to 0, right? So when you use the intermediate value theorem, you prove that the equation has at least one solution, because you're gonna cross the x-axis at least one time, right? So here in this case, I have this f of x, this equation 2x minus 1 minus sine of x equal to 0. So if you do, the interval is 0 pi, right? You have this interval 0 pi. So if you do f of 0, there will be 2 times 0 minus 1 minus 0. Sine of 0, or sine of the angle 0, of course, is 0. 2 times 0 is 0, so that will be negative 1. So you see f of 0 is negative 1, right? Now f of pi, that will be 2 times pi. Oh, no problem, Emma, I got you, thank you. So 2 times pi minus 1 minus sine of pi. Sine of the angle pi, that's negative 1. So you're going to have actually f of pi, that's 2 pi minus 1 minus negative 1. So that'll be plus 1. So that's equal to 2 pi, right? Minus that will be a plus. So that's negative 1 plus 1 cancel out. So that's just 2 pi. So you see f of 0 is negative and f of pi is positive. So you go from negative to positive. It means that you're going to cross at least one time the x-axis. And if you cross the x-axis, it means that you have a solution of f of x equal to 0, right? So by the intermediate value theorem, because f of 0 is negative and f of pi is positive, so we have opposite sign. So then by the intermediate value theorem, there exists at least one solution of, at least one solution of f of x equal to 0. Right? So that's the first step. So I just proved that I know by the intermediate value theorem there exists at least one solution. Well, of course, so the exercise, guys, is to prove that the equation has exactly one, right? Show that the equation has exactly one, right? But the intermediate value theorem, with the intermediate value theorem, actually we can prove that the equation has at least one, okay? But that's not exactly what we want, right? We need to prove that the equation has exactly one solution, not just at least one solution, right? So that's why we need the second step. So this is intermediate value theorem to show that there exists at least one solution, right? So you see, guys, with the theorem, by like this intermediate value theorem, you know there exists a solution, but you don't know the exact the exact value of the solution, right? It's, you know, it sounds kind of weird, but you don't know exactly what's the solution, but you know that it exists, right? You know it's there, but you don't know exactly the value of the solution, right? Anyway, so that's the first step. So I can prove that there is at least one solution. Now, second step, we said in the step 2, we have to show that the equation has no more than one. Okay, so no more than one solution. That's actually what we did the last week using the Rolle's theorem. So in the step 2, I'm going to use the Rolle's theorem. So in this step 2, so we're going to use Rolle's theorem to prove or to show that the equation has no more than one solution. Right? So I'm going to show you.
Professor,
yes. Yeah.
That's all of step 1 that what we just did. How come it's so long though? Can't you just do like the equation that you did here and then that's it?
You mean for the which the first step, or?
Yeah, the first step. Can't you just where you put f of 0 equals 2 times? Can you just start from there and that's it?
Yeah, you can just say. Yeah, you can just say like f of 0. You can just say f of 0 is -1. That's negative, and f of pi is positive. So then, by the intermediate value theorem, there exists at least one solution.
Okay.
I mean, here I try to explain the idea of the theorem, right? This is, you know, this thing here. Where is it? So I mean, the graphs. You see the graphs here. I mean, that's just to explain the idea, right? This intermediate value theorem, right? But all you have to do actually is just to evaluate this f of 0, this f of pi. One is negative, one is positive, and then you conclude by the intermediate value theorem there exists at least one solution.
Oh, okay.
Okay. Yeah. Here, I mean, the graphs is just to explain the idea, right? Now, this is the second step. So this intermediate value first step, we prove that there at least one solution. Now I'm going to show that there is no more than one solution. So that's what we did actually last week. So we said to prove that the equation, for example, has no more than solution, we have to use a proof by contradiction, right? So that's where we use proof by contradiction. Right. So what I'm going to do, so how does it work, this proof by contradiction? So first we start with the hypothesis. So I'm going to suppose, so my hypothesis would be that, so the hypothesis is that the solution has, let's say, two different solutions. So the equation has two different solutions. And then I'm going to use Rolle's theorem to deduce a contradiction. And once you have a contradiction, it means that the hypothesis is wrong. It means that you cannot have two different solutions. And if you cannot have two different solutions, it means that you have no more than one solution. Okay, so now I'm going to use, I'm going to use Rolle's theorem to get a contradiction. Okay, so I have this hypothesis that I have two different solutions, right? So then let's say I have A and B. So let A and B my solutions. So solutions of my equation, right? My f of x equals to 2x minus 1 minus sine of x. Okay, so I have these two different solutions, a and b. So it means that f of a is 0, right? And f of b is 0, okay? Because both are solutions. And that's exactly the hypothesis in the Rolle's theorem. So in Rolle's theorem, we need f of a to be equal to f of b, right? So in Rolle's theorem, remind you the Rolle's theorem, guys. Here's my Rolle's theorem. We said in the as a hypothesis, we need f of a to be equal to f of b, right? F of x differentiable says that f of a is equal to f of b, right? So then here I have this f of a equals to f of b, which is equal, both are equal to 0, right? So now what does it say, this Rolle's theorem? The Rolle's theorem says that, so then by Rolle's theorem, okay, there exists a number c in the interval ab, open interval ab, says that f prime of c is 0. So it says that, again, guys, this is similar to the problem 5 in the homework 9, okay? Says that f prime of c is 0. All right, but on the other hand, if you want to solve f prime of x equal to 0, so on the other hand, you know, f prime of x is equal to, so here's my f of x, is 2x minus 1 minus sine of x. So derivative of 2x is 2 minus 1, derivative of 1 is just 0, so it's 2 minus 0, and derivative of sine is cosine, so it's 2 minus 0 minus cosine of x. Now, if you want to solve f prime of x equal to 0, so then you would have 2 equals to cosine of x, right? But that's impossible. I mean, cosine of any angle, it's always between -1 and +1. So this is impossible. Okay, but the Rolle's theorem says that there exists a c for such that the derivative at c is 0. But we just tried to solve the derivative equal to 0, and we got no solution, right? It's impossible that my derivative is equal to 0. So that's a contradiction, right? So there's a contradiction between the existence of a number c so that the derivative of f at c is 0, and the fact that I cannot solve, you know, if I try to solve my derivative equal to 0, then I would get no solution. There is no solution to my derivative equal to 0. So that's a contradiction. So that's why we have a contradiction between Rolle's theorem. And on the other hand, when you try to solve the derivative equal to 0, you get no, there's no solution, right? So this is impossible. So no solution to f prime of x equal to 0. But the Rolle's theorem, again, the Rolle's theorem says that there's a number c for which the derivative is 0, right? So that's a contradiction. So if you have a contradiction, it means that the hypothesis is wrong. And the hypothesis says that I have two different solutions, right? So if this is wrong, it means that we cannot have two different solutions. So it means that we'd have no more than one solution, right? So then conclusion. So from this is step 2. So conclusion. So the equation has no more than one solution. Has no more than one solution. So you see, guys, how we combine this. So first, we had this intermediate value theorem to say, well, I have at least one solution, right? But then I'm using this Rolle's theorem to say, well, I cannot have more than one solution, right? So if you combine the two facts, so fact 1 is that I can have at least one solution. And the second fact is that I can have no more than one. So then if you combine both facts, then the conclusion, this is the step 3, is that the equation has exactly one solution. So combine. So step 1 and step 2. Okay, to deduce that the equation well, it's 2x minus 1 minus sine of x equal to 0 has exactly one solution, has exactly one solution. All right. And again, guys, this is kind of, I mean, it's a kind of like a miracle, right? Because, you know, using these theorems, you just prove that there is a solution, there is exactly one solution, but still you don't know, you know, the exact value of the solution. You know, there is one, okay, there is exactly one, but you don't know the exact value of the solution, right? So this is kind of, I mean, it's very strong, right? You know, you prove that there exists a solution, but you don't know even the value of the solution, right? Any question, guys? So again, this is similar to the problem number 5 in the homework, right? Where you have to prove that the equation has exactly one solution. Okay, perfect. Thank you, Juanita. All right, guys. So this is like like one of the application of the Rolle's theorem. So you have like equations, and you can use this Rolle's theorem and the intermediate, and you can combine it to this intermediate value theorem to say that your equation has like exactly one solution, or etc. Anyway, now let me just move to like a generalization of when the homework is due. It's next Monday, Ibrahima. It's next Monday, not today. It's next Monday, right? So the homework, again, homework number 9, it's due next Monday. Sure. Okay, guys. So I'm gonna now I'm gonna move to the mean value theorem. This is the last. So this is the last theorem in this section. So this is sort of a generalization of the Rolle's theorem. So what does it say? The mean value theorem. So the mean. Yeah, sure. All right. Okay, I'm gonna be in trouble, I guess. So let's see. Come on. All right. So now I guess I have to. Sorry. Here. Sorry, I have to zoom out, I guess. Sorry. Come on. Well, sorry. Here. All right. Anyway, so okay, sure, sure, Juanita, no problem. Yes. Okay. Okay. Thank you, Ibrahima. So yeah. So I was saying. So we're gonna generalize this Rolle's theorem. So that will be now. So now we're gonna have this mean value theorem. So what does it say? This mean value theorem? Well, it's again, it's just a generalization of this of the Rolle's theorem. So you suppose that you have a continuous function. Suppose f of x continuous on this closed interval AB, All right, and also differentiable on the interval AB. So, well, then the theorem says the following. So the conclusion is the following. Okay. So you see here the difference between this mean value theorem and Rolle's theorem. In Rolle's theorem, let me see here. So where is it? This Rolle's theorem. In the Rolle's theorem, we have this. Well, of course, we have a continuous, f continuous, a differentiable, but then we also have this condition that f of a is equal to f of b, right? This is one of the hypotheses in Rolle's theorem. So we have f continuous differentiable and also f of a is equal to f of b. Then you have the conclusion, right? Now, in this mean value theorem, so we remove the hypothesis that the f of a is equal to f of b. Okay, so in this mean value theorem, all you need is f of x to be continuous and differentiable. Okay, so there's no we remove the hypothesis that f of a is equal to f of b. Okay, so then the conclusion is that they exist C in the interval AB says that the derivative of f at C is equal to f of B minus f of A over A as over B minus A. All right, so this is the conclusion of the theorem. So theorem says that whenever you have continuous function differentiable on this interval AB, then you know that it exists a C in the interval AB such that this derivative of f at C is equal to this f of B minus f of A over B minus A. So first, before the idea of the theorem, let me just explain the relation with the Rolle's theorem. So if f of A is equal to f of B, then this f prime of C would be 0, right? Relation with Rolle's theorem. So as I said, in Rolle's theorem, we make this hypothesis that f of A is equal to f of B, right? So in Rolle's theorem, we have the hypothesis that f of A is equal to f of B, right? We have the hypothesis that f of A is equal to f of B. So then if f of A is equal to f of B, you can see that f prime of C would be 0. So then f prime of C, then this, then f prime of C, which is supposed to be f of B minus f of A over B minus A, that will be equal to 0, right? Because f of A is equal to f of B, right? F of A is equal to f of B, so that will be 0 over B minus A, and that will be equal to 0, right? So this is a sort of generalization of Rolle's theorem, right? Because in Rolle's theorem, this have this hypothesis that f of A is equal to f of B, and so you can see here if your f of A is equal to f of B, your f prime of C is going to be 0. Okay, so that's why this mean value theorem is sort of a generalization of Rolle's theorem. All right, now what's the idea of this? So why do we have the existence of such a C? So we are saying you have a function, continuous differentiable on this interval AB, then there exists a C, says that this C is equal to this f of B minus f of A over B minus A. So first, what's f of B minus f of A over B minus A? So, you have, so you have your graph. So let's say this is A, and this is f of A. All right, and here's B. All right, and f of A is not necessarily equal to f of B, right? So here's somewhere f of B. Okay, and let's say this is your f of x. Okay, this is my f of x. All right, so first, so what does this number here represent? F of b minus f of a over b minus a. Well, that's the slope of the line which passes through f of a, and b f of b, right? So if you take this line, you know, which passes through the points a, f of a, and this line here, right? So what I'm saying is that the slope of this line is exactly, so the slope of the line which passes through the points a, f of a, and b, f of b. So the slope of this line would be exactly this, the number f of b minus f of a over b minus a, right? So all I'm saying, guys, that the slope of the line passing through these 2 points, that's exactly my f of b minus f of a over b minus a. All right. Again, this is here's a f of a, and this is b f of b, right? Anyway, so what we are saying is that there exists a c in this interval. So there's a c here somewhere. All right, says that f prime of c is equal to you know, to this slope, right? To this f of b minus f of a over b minus a. And remember, what's the interpretation of f prime of c, right? What's the interpretation of the derivative at the point? So that will be the slope of the tangent line. So this f prime of c, that's supposed to be the slope of the tangent line to the function f at c, right? So you see this tangent line to f of x at c. So the slope of this tangent line, that's exactly my f prime of c. Okay. And what I am saying, so what does the theorem say is that the slope of the line passing through the AF of A, the BF of B, you know, so the slope of that line would be equal to the slope of this tangent line to the function f at c, to this blue line here. Okay, and these 2 lines, they have the same slope, right? The blue one, right, and this one here. Okay. So the 2 lines, they have the same slope. Okay. All right, so that's the mean value theorem. So let me show you examples how we use this mean value theorem. So examples. So first example, so this example is similar to the problem number, let's see, problem number 7 in the homework. So first problem here. So this is similar to the problem 7 in the homework 9. All right. Well, so suppose, so what I'm gonna do, I'm gonna suppose that you have a function f, so f of x continuous, differentiable, and the derivative of f of x, f prime of x, is always between, let's say, 4 and 6 for any x. Okay. So what I'm saying is, so the hypothesis is that the derivative is always between 4 and 6. for any x. F prime of x is always between 4 and 6. Okay.
Professor, I have a
Yes.
question.
Yeah.
Sorry. What is the derivative of xy? Is it just xy?
A derivative of x times y?
No, of xy together.
Oh, xy. Well, you have to use the product rule. So that will be x. That will be 1 times y plus x times y prime. So it should be y plus xy prime.
Y plus xy prime.
Y plus xy prime, right? Yes. That's the product rule.
Oh, okay. Thank you.
Sure. Okay, guys. So this is this is our hypothesis that the derivative is always between 4 and 6. And let's say you want to show that let's say f of 3 minus f of 1 is always between 8 and 12. Okay. So again, the hypothesis is that your f prime of x is between 4 and 6, and you have to prove that your f of 3 minus f of 1, that would be between 8 and 12. All right. So the thing is, so we're gonna use, of course, this mean value theorem, right? So we have this interval, let's say 3, 1, 3. So the idea is, of course, to use this mean value theorem. Okay, on this, let's say, interval, on the interval 1, 3. So on the interval 1, 3, because we are interested in the value of f of 3 and f of 1. So I'm going to use the interval 1, 3. All right. So I mean, it's just one line actually. So on this interval 1, 3, you know that there exists f prime of c. So the answer here. So on the interval, on the interval 1, 3. Okay. So the mean value theorem says that. So by the mean value theorem, so what does it say? The mean value theorem, it says that on this interval 1, 3, there exist. So the conclusion of the theorem is that there exists a c in this interval 1, 3 or ab, says that this f prime of c is equal to this f of b minus f of a, etc. So here, so by the mean value theorem, there exists c in the interval. I'm interested in the interval 1, 3, such that f prime of c is equal to f of 3. That's so 1 would be a, right? That's my a, and the 3, that's my b, right? So f of b minus f of a, which is 1, over b, which is 3, minus a, right? So there exists this c, which is equal to f prime of c. So f prime of c, which is equal to, so this f of 3 minus f of 1 over 2, right? Right, but then that's the mean value theorem. But then we have the hypothesis. So in the problem, we suppose that your f prime of x, the derivative is always between 4 and 6. So the derivative of f is between always between 4 and 6. So this f prime of c is always between 4 and 6. So f prime of c, so then this f prime of c is between 4 and 6. But what's f prime of c? F prime of c is f of 3 minus f of 1 over 2 between 4 and 6. So to get rid of the 2, you just multiply by 2, right? By 2 here, by 2, and by 2. So here, this 2 cancel out. So then your f of 3 minus f of 1 would be between 8 and 12, right? And that's exactly what we need to prove. We need to prove that, show that f of 3 minus f1 is between 8 and 12, right? So, and that's exactly what I get here. So that's a fine answer here. This is my f of 3 minus f of 1 is between 8 and 12, right? So it just you know, it's an application of this mean value theorem. You say that there exists a C such that this f prime of C is equal to, because we are interested in f of 3 minus f of 1, right? We are interested in this. We have to prove that f of 3 minus f of 1 between 8 and 12, right? So that's why I'm using the interval 1, 3, because we are interested in f of 3 minus f of 1. Right. Another example, guys, which is very similar to the problem number 8 in the homework. So this is another example. So this is example 1. So this is example 1, yes. So here's an example number 2. So example number 2. So this is similar to the problem 8 in the homework 9. Yeah, sure, Ibrahima, yes. Mm-hmm. Okay. I can zoom out if you want. Oops, sorry. Let me just zoom out. Probably it's better for you. Mm-hmm. So yes, so similar to this, the problem 8. This is problem 8 in the homework 9. Right. So what does it say? The problem. So the example is the following. So let's say, so we have this f of x differentiable. F of x be a differentiable function. So we have this differentiable function, continuous, etc. So it satisfies the the hypothesis in the mean value theorem and differentiable function. And suppose, let's say you have this function f of x differentiable, and you suppose that you know that let's say f of 1 is let's say 5. Okay, f of 1 is 5. And you know that, let's say, f prime of x, the derivative of your function f is always, let's say, so this is, let's say f prime of x is larger or equal, so this f prime of x is larger or equal to, let's say, 7, okay, for any x. Okay, for any x, let's say in the interval, let's say 1, 3. Okay. So in this interval 1, 3. All right, so we have two hypotheses. So we have this function f, and you know that f of 1 is 5, all right? And you know that the derivative of f f prime of x is always larger or equal to 7. So the slope of your tangent lines to f of x for any x between 1 and 3, the slope would be always larger or equal to 7. Okay, so we have these two hypotheses. So the question is, how small can, let's say, how small can f of 3 possibly be? So the question is, how small can f of 3 possibly be? All right, so we have this interval again. You have this interval 1, 3, right? Here's your interval at 1, 3. You know that f of 1 is 5. And you know that the derivative is always larger or equal to 7. So you want to find like a lower bound for f of 3, right? So you wanna estimate the f of 3. So the question is, how small can f of 3 possibly be, right? Well, so how can we answer such a question? Well, I'm going to use, of course, the idea is to use this mean value theorem. So the answer, so let's try to use the value theorem. So the answer, come on, this is, all right. All right, so this is the answer. So we're going to use so we have this f of x, so we're going to use the mean value theorem on this interval 1, 3, right? We have this interval 1, 3, right, on the interval 1, 3. So what does it say, the mean value theorem? Of course, your f of x is differentiable, etc. So the conclusion of the theorem is that they exist. So then they exist C in this interval 1, 3. 1, 3 says that f prime of C is equal to f of 3. So the, oops. Okay, so what is it? I think I lost the board for some reason. I think there's a problem with Zoom, right? It's a problem. I don't know. Okay, so okay, so let me write again the last the example, guys. I'm sorry. I think there's a problem with Zoom. All right, so the example was so we had this f of x, right, differentiable. We know that f of 1. We said f of 1 is I think 5, right? And we said f prime of x is larger or equal to 7 on this interval 1, 3, right? And so the question is, how small can f of 3 possibly be? All right. So we said we're going to use, of course, the mean value theorem. On this interval 1, 3. Okay. So what does it say? What's the conclusion of mean value theorem? So mean value theorem, it says that so there exists a C in this interval 1, 3, says that f prime of C is equal to f of, so A would be 1, and of course C would be my B, right? That's my interval. So then f of B minus f of A over B minus A. Okay, that's my f prime of C. So then this f prime of C would be equal to, so I don't know what's f of 3, right? I wanna estimate f of 3, right? So the question is, how small can f of 3 possibly be, right? So I don't know f of 3. I want to estimate f. I want to find like a lower bound for f of 3. So f of 3 minus f of 1. I do know the value of f of 1, right? F of 1 is 5. So it's minus 5 here over 3 minus 2 in the bottom. That's 2, right? That's my f prime of c. Now, so I used my first hypothesis. I used the fact that f of 1 is 5 right here, right? This f of 1 here is 5. Now, I want to use the second hypothesis. The second hypothesis is that the derivative is always larger or equal to 7. So this is f prime of c. That's the derivative of my f at c. This is always larger or equal to 7, right? This is the hypothesis, second hypothesis, right? My f prime of c is larger or equal to 7, right? Because I know that my derivative is always larger or equal to 7 on this interval 1 thing, right? So f of t minus 5 over 2 is larger than 7. All right, so now I'm going to solve for f of t because I want to estimate f of t, right? So I want to solve for f of t. So we have f of t minus 5 over 2 larger than 7. So I'm going to multiply by 2 both sides. So times 2 here, times 2 here. So this 2 here cancel out. So then my f of t, so then my f of t minus 5 is larger than 14. I'm going to add 5 both sides. So then f of t would be larger or equal to 19. All right. So how small can f of t possibly be? Well, the answer would be 19. Okay. So to answer the question, so how small can f of t possibly be? Well, the answer would be 19, right? Because f of t, it has to be, f of t has to be larger or equal to 19. So 19 would be like the lower bound, the lower bound for f of t, right? That's the smallest value of that f of t can be, right? That's the 19. Any question, guys? So did you see how I apply this mean value theorem?
Yes.
All right. Okay, so that's actually we are done with this section. This is the last theorem in this section. So I guess we can move. Well, before moving to the next section, so I'm gonna give you an exercise, a similar problem, guys, and then we're gonna move to the next section. Okay, so here's an exercise, similar problem, exercise. All right, so let's say f of x differentiable, of course, let f of x be a differentiable function, differentiable, okay, differentiable function. Suppose that f of 2 is equal to, let's say, 4, and f prime of x is actually, let's say, less or equal to, let's say, 6 for any x. So in the interval to let's say 2, 7. All right. Now the question is, how large can f of 7 possibly be? All right. So you have two hypotheses, guys. You have your f of 2 is equal to 4, and your derivative is always less, is always less than 6, right? In this interval, your interval is the 2, 7, right? And the question is, how large can f of 7 possibly be? Okay, I mean, this is kind of, well, a little bit different from the previous example. In the previous example, the question was how small can f of 3 possibly be? So here it's how large can f of 7 possibly be, right? I'm gonna give you a couple of minutes to think about this exercise, guys. So this is very similar to the previous problem or the previous example. All right, guys. Any guess how large can f of 7 possibly be? What will be the largest possible value for f of 7? So you know that your f of 2 is 4, and your derivative between 2 and 7 is always less than 6. Oh, Adrian, you said 24? Yes, yes, very good, Adrian. Yeah, absolutely. So yeah, 24, absolutely. So the idea is, of course, use this mean value theorem. So you have this interval 2, 7. So the 2, that's A. The 7, that's your B. All right. So okay. So here's the answer. So the interval is 2, 7. Right. So the 2, this is my A, and the 7, that will be my B. Now, so what does it say? The mean value theorem. If you apply the mean value theorem on this interval, so by the mean value theorem, that exists C in the interval 2, 7, right? That's my interval, such that f prime of C is equal to f of B, so that's f of 7, minus f of A, so that's f of 2, over B minus A, so it's 7 minus 2. Right. Now, okay, that's my mean value theorem. Now I'm going to use the first hypothesis. I know that f of 2 is 4. Right, that's my first hypothesis. I know that f of 2 is 4, so I can replace this f of 2 with 4. So so then my f prime of C would be f of 7. I'm trying to estimate f of 7, right? So I don't know exactly what's f of 7. I'm gonna try to estimate it, right? So minus f of 2. I do know what's f of 2. That's given in the problem. It's 4. So minus 4 even over 7 minus 2. That's 5. Okay, and then there is another hypothesis in the problem, is that the derivative is always less than 6, less or equal to 6, right? So your derivative, this is the derivative, f prime of C is the derivative, right? Derivative of f at C. So this is always less or equal to 6. Okay, because that's a hypothesis in the problem, that the derivative is always less or equal to 6. So this f prime of C is less or equal to 6. So then I have like f of 7 minus 4 over 5 less or equal to 6, right? So I wanna solve for f of 7, right? So then I'm gonna multiply by 5 by 5 by 5. So Adrian, it's actually 34. It's not 24, right? So the 5 here cancel out. So that's f of 7 minus 4 less or equal to 30, right? And so plus 4 both sides. So then your f of 7 is less or equal to 34. So the upper bound for f of 7, right? The upper bound would be 34. Okay. So to answer the question, how large? So to answer the question, so how large can f of 7 possibly be? So that would be 34. Okay, so how large can f of 7 possibly be? All right, so f of 7 has to be less or equal to 34. So the largest possible value for f of 7, that's 34. So the answer is 34. And this 34. All right. Makes sense to you guys? Any question?
No, it makes sense.
Okay, perfect. All right, so actually, so then we are done with this section. So I'm gonna move to the section. So I'm gonna try to combine actually sections 3.3 and 3.5. I think they're the most important sections in this chapter 3, sorry. So so I'm gonna probably move to the next page. So this is section. So I'm gonna combine section 3.3 and 3.5, right? So we're gonna use the derivative, to graph functions. So I'm gonna explain the relation between the derivative and the shape of the graphs. So derivatives and the shapes of curves or graphs. Right. I think this section is kind of very. It's a short section. All right. So we're gonna see how to use the derivative to find, the maximum, minimum, when the function is decreasing, etc., etc. So there are a lot of informations you can get from the derivative. All right. So let's start with increasing, decreasing functions. So when the function is increasing and when the function is decreasing. Probably, guys, we can probably take a break of 5 minutes. All right, and then we'll start with this section 3.3 and 3.5. All right, so let's
Okay.
take a break of 5 minutes. All right. I will be back at 7:35.
Okay, Professor.
Mm-hmm. All right, guys. So let's continue with this derivative on shapes of graphs. So first, I'm gonna start with when the function is increasing and when the function is decreasing. All right. So this is actually a theorem. So if the derivative is positive, so if f prime of x is positive on an interval I, okay, so then f is increasing, f of x is increasing on I, right? And if the derivative is negative on the interval I, then the function would be negative on an interval I, then f of x is decreasing on I. All right, so that's because the idea is you need to think of, so you have to think of the f prime of x of the derivative as the slope of the tangent line. So it's like, so you have, let's say, this graph. All right, so here, let's say your function f of x. All right, this is f of x. So on this first interval, you see on the first interval, if you take the tangent, if you take the tangent lines, the slope, they are actually positive. So that's why the function is increasing. So here the slope is positive. So this is why the function f, so f of x is increasing. All right. Now on the second interval, so here, if we take the tangent line, the slope of the tangent line, they are negative, right? This is the slope here is the blue. The slope of these blue lines here are negative. So the slope here is negative. The slope of the tangent line is actually negative, and that's where your f of x is decreasing, right? So again, guys, you have to keep in mind that the derivative is actually the slope of your tangent line to the function, right? So if your derivative is positive, it means that the slope is positive, right? So then your function is increasing. And if your derivative is negative, it means that the slope is negative. So then your function is decreasing, right? So for example, let's say you want to find the interval of increase and decrease. Find the interval where f of x is increasing or or decreasing. Right? So let's say you have this function f of x. So let's say f of x is equal to, so let's say f of x is equal to x squared minus x on the interval, on the whole number line. So on the interval negative infinity, positive infinity. Okay, so you want to find the intervals where the function is increasing, decreasing. So we have to study the sign of the derivative, right? So we have to determine when the derivative is positive and when the derivative is negative, right? So, so there are actually two steps. So step one. So in the first step, you have to solve f prime of x equal to 0. All right. And the second step, you have to, so you have to make the chart, the sign of the derivative. Okay, chart of the sign of f prime of x. Okay. And so where, on the interval where the derivative is positive, the function is increasing, and where the derivative is negative, the function is decreasing, right? So for the first step, for the step one, so we need to solve f prime of x equal to 0, right? So step one, I'm gonna solve f prime of x equal to 0. So what's f prime of x? Well, f of x is it's x squared. So derivative of x squared, it's actually 2x. And then there is minus. So here's my minus. And then what's the derivative of x? It's just 1. So it's 2x minus 1. All right. And I'm going to solve f prime of x equal to 0. So that's 2x minus 1 equal to 0. So I'm going to solve for x. So then here's my plus 1. So that's 2x equals to 1. And so you divide by 2. So then your x would equal to half. So that's where the derivative is 0, right? So again, this is a solution for f prime of x equal to 0, right? So I solved f prime of x equal to 0. So now in the second step, I can make like this chart of the sign of f prime of x. So the chart, so how does it work? So this is step 2. So this is my chart. Okay, so you have your, the domain here is the whole number line, right? It's negative infinity to positive infinity. So we have, my interval, the domain is, so it goes from negative infinity to positive infinity, right? That's my domain. Anyway, so in this, on this chart, guys, you have to put where the solution of f prime of x equal to 0. So f prime of x equal to 0 when x is equal to half, right? So I'm gonna put half on this number line, okay, from negative infinity to positive infinity. So that's where my derivative is 0. So this is a solution of f prime of x equal to 0, right? Now, now I'm gonna put my here. So first, in the first row, I'm gonna put my I'm gonna put f of x, and in the second row, I'm gonna put f prime of x, which is f prime of x. That's 2x minus 1, right? That's my f prime of x, 2x minus 1. All right, so then, so let's say this is here, this is the line which represents x equal to half. All right. So we know a solution of f prime of x equal to 0 is when x equal to half. So I'm gonna put like I'm gonna put a 0 here, right, on this line, because when x is equal to half, f prime of x, you see here, f prime of x, this f prime of x is gonna be 0. So that's why I have this green 0 on this line, right? Because that's where the derivative is 0. Now, you see, guys, I have like two intervals. I have this first interval from negative infinity to half, and I have a second interval from half to positive infinity, right? I have like two intervals. Now, I want to determine the sign of the derivative, right? So what I'm going to do, I'm going to just pick a random number, on this first interval, like from negative infinity to half. So for example, I can pick, let's say, -1. And here, I'm going to pick a number between half and positive infinity. So for example, I'm going to pick 3. Okay. And what I'm going to do, I'm going to plug my -1. Let's say I pick -1, right, on the first interval. So I'm going to plug -1 here. Okay, in the 2x minus 1 in the derivative. So if my x is -1, then 2 times -1, that's -2, minus 1, that's -3. So it's going to be negative. So what I'm saying, guys, is that on this first interval, my derivative is going to be negative, right? Because, so what I did, again, I plugged the -1 in the f prime of x in the 2x minus 1, and I got -3, right? So that's negative. So that's why I have this negative in the second row. Now, in the second interval, I picked from half to positive infinity, I picked 3, right? So I'm going to plug 3 in the derivative. So that's 2 times 3. That's 6 minus 1. That's 5. So it's positive 5. So here on this second interval, we're going to have positive. So my derivative is going to be positive from half to positive infinity, and it's negative from negative infinity to half, right? So now the question is, what about the function f itself, right? So we said if the derivative is negative, then the function is going to be decreasing. So on the first interval from negative infinity to half, the function is decreasing, right? And then on the second interval from half to positive infinity, the derivative is positive, right? So then the function is increasing, right? So
I have a question.
yes, yeah, please.
Why you said where you got 1/2 at the bottom, you
half,
say equal to 0?
the 1/2, that's from the first step. You remember first step, I had to solve f prime of x equal to 0.
I'm saying where you have f prime of x equal to 2x minus 1, and you have where there's a green thing.
The green 0.
1/2 is not part of the solution
Here?
or what?
This
Yes.
0. You're talking about this 0, right?
Yes.
That's because when x is you see this x here, this x is half, then 2 times half minus 1 is 0. So that's why I have this 0. This 0 means that my derivative would be 0 at half. So this 0 means that f prime of half is 0. That's why the 0 is on the line which represents the coming from the half. It's the line which represents half, right? Okay. Does it make sense? All right.
Yeah, thank you.
Okay, sure. So yeah, so then the answer to the question is so the interval of the answer to the question, so f of x is increasing on half positive infinity and decreasing on negative infinity half. All right. Any question, guys? Yeah. So you see again how I got this interval of increasing and decreasing, right? So first step, I have to solve where the derivative is 0. I have to solve f prime of x equal to 0. And then the second step, I have this chart. On the chart, we put the solutions we got in the first step, right? And then you have to, pick a random number, random numbers in the intervals, and you have to plug them in their derivative to see if the derivative is negative, if the derivative is negative or positive, right? Okay, so here's an exercise, guys. Unless there's a question. Okay, so here's an exercise. So same thing. Find. So exercise. So find the intervals of increasing. So the intervals of increase and decrease of f of x. So let's say your f of x is equal to, let's say 2x cubed minus 2x squared minus 2 minus 2x plus 1. Okay, that's your function f on the interval negative infinity, positive infinity. Okay, so guys, you have to find where the function is increasing or decreasing on this interval negative infinity, positive infinity. All right, so I'm gonna give you a couple of minutes to think about this exercise. Again, there are 2 steps. First step, you have to solve the derivative equal to 0, right? F prime of x equal to 0. And then the second step would be to make this chart, and with the sign of the derivative.
Professor,
Yes.
step one will be equal to 1.
Well, what's equal to 1? Sorry.
Step 1.
Yeah, I think so. Yeah.
Okay.
Yeah, one of the solution would be 1. Yes.
Okay.
Sure. Very good. All right. So,
Hello?
any guess? Yes.
Professor,
Yeah.
I have a question. Once
Yeah.
you get the value of x, you replace it on the f prime
Derivative.
of x.
Yeah. F prime. Yes. The derivative. Yes.
Okay, for the sign, right?
Yes. Yes.
Okay.
All right, guys. So do you know where the function is, let's say, decreasing? Any guess?
It's decreasing between -1/3 and
Mm-hmm.
1.
Yes. Yes, Ibrahima. Very good. Exactly. Yes.
And minus infinity to -1/3, it's increasing.
Mm-hmm.
And from 1 to plus infinity increasing.
Yes. Very good. Absolutely. Very good. That's correct. So yes. Um, so first step. So step one. So we have to solve this f prime of x equal to 0. So first we have to compute f prime of x. This is your f of x. So first you have 2x cubed. You keep the constant derivative of x cubed. You bring down the power 3 times x and you decrease the power by 1. So it's 3x squared. There's a minus. So here's my minus. You keep the constant times derivative of x squared. Bring down the power times x and decrease the power by 1. So it's just 2x minus 2 times, you keep the constant 2, derivative of x is just 1. So minus 2 times 1 plus, now we have a constant by itself, and you have a constant by itself, its derivative is 0. So actually f prime of x, it's 6x squared minus 4x minus 2. So we have to solve f prime of x equal to 0. 6x squared minus 4x minus 2 equal to 0. That's a quadratic function, quadratic equation. So we have to use a quadratic formula. So your x is minus b. So it's minus -4 plus or minus square root of b squared. That's -4 squared. That's 16 minus 4 times a. That's 6 times c. That's -2. The whole thing over 2a, it's 2 times 6. So this is minus minus, there'll be a plus. So your x, it's actually negative, of course, negative minus -4, that would be a plus 4. So this is 4 plus or minus square root. So 4 times 6, it's 24. 24 times 2, it's 48. 48 plus 16, that's 64. And so this is square root of 64 over 12. So then x, it's 4 plus or minus square root of 64, that's 8 over 12. So there are two solutions. So first solution is 4 plus 8 over 12. That will be 12 over 12. That's equal to 1. Or x is 4 minus 8 over 12. That will be negative 4 over 12. You have to reduce your fraction, divide by 4. So yeah, then your x is actually divided by 4. So then your x is, here's by 4. Here's by 4. So then your x is -1/3. All right, so we got two solutions, guys, right? So x equal to 1. So this is solutions, again, solutions of f prime of x equal to 0, right? So we got +1 and we got -1/3. So now in the chart, So this would be the step number 2, the chart. So you start with your number line. So my domain it goes from negative infinity to positive infinity, right? And then you have to put your solutions from the step 1, right? So we got positive 1 and negative 1/3. So first I have negative 1/3, and then I have 1, right? Those are my solutions of f prime of x equal to 0. Now, first row, that will be my f of x. Here's my f of x. And second row, that will be f prime of x. So f prime of x is equal to, we just compute f prime of x. It's 6x squared. So it's 6x squared minus 4x minus 2, right? And then I have this line coming from negative 1/3 and this line coming from 1. And then I have to put 0 on these lines here, 0 here, and 0 here because f prime of negative 1/3 is 0 and f prime of 1 is 0, right? That's why I have these two zeros. Now, I have 3 different intervals, right? I have this first interval from negative infinity to negative 1/3. I have the second interval from negative 1/3 to 1, and I have the third interval from 1 to positive infinity, right? Now, I'm gonna try to figure out the sign of f prime of x. So I'm gonna pick a random number, like from the first interval. So first interval, I'm gonna pick a very small number here. Let's say negative 1, right? That's between negative infinity and negative 1/3. Between negative 1/3 and 1, I'm gonna pick 0. And between 1 and positive infinity, I'm gonna pick 2, right? And then I'm gonna plug those numbers here in the f prime of x. So if you plug negative 1 in 6x squared minus 4x minus 2, x squared, negative 1 squared, that's positive 1. So it's 6 minus 4 times negative 1, that will be plus 4. So it's 6 plus 4 minus 2, that would be positive 8. So what I'm saying is that the derivative on the first interval is actually positive. Now, on the second interval, I picked 0, right? This 0 here, this one here. So if you plug 0 in the f prime of x, you get 0 minus 0 minus 2. So that's negative 2, that's negative. And finally, the third interval, I picked positive 2. If you plug positive 2, so there'll be 2 squared, that's 4 times 6, 24. Minus 8, that would be 16. Minus 2, that would be 14. So that's positive 14, right? So this is positive. Now, on the first interval, derivative is positive. So my function f would be increasing here. And then it's negative, so it's decreasing. And then it's positive. The derivative is positive again. So then my function is increasing. So yes, as Ibrahima said, so the answer, the question is the following. So the function f, so f of x is increasing on so negative infinity to negative 1/3 and positive 1 to positive infinity, and decreasing on negative 1/3 positive 1. All right. Any question, guys? That's clear. All right.
It's clear, Professor.
Okay, thank you. All right, so then let's move. So this is for when the function is increasing, decreasing. Now we want to find the local maximum and the local minimum, right? So, I mean, you can even see it here from the chart. You know, in this chart, we are saying that your function is increasing and then it's decreasing, right? So this actually negative 1/3, right? That will be because it's increasing here and then it's going to decrease after the negative 1/3. So the negative 1/3 is going to be a local maximum. Now for positive one, so you can see here the function is decreasing and then it's going to increase, right, at positive 1. So then this positive 1 would be a local minimum. So the idea or the theorem is the following. So if the derivative change the sign, so this is a theorem, and you can even see it from the chart. So this is a theorem. So if so suppose, of course, suppose f prime of a is equal to 0. Suppose that f prime of a is equal to 0. So a is a critical point. So if first the first case is that if f prime of a changes the sign. So if f prime of x changes the sign from plus to minus, or from positive, the sign from positive to negative at a, then f of x has a local, so it goes from plus to minus, so it's increasing and then it's decreasing, so f of x has a local maximum at a. If the f prime of x changes the sign from negative to positive, so this is the second case. So if f prime of x changes the sign from minus to plus, from negative to positive at a, then f of x has a local minimum at a. And of course, the third case is when the f prime of x doesn't change the sign. So if it doesn't change the sign, so then f of x has no local maximum or minimum at a. So if f prime of x do not change, so it doesn't change the sign at a, okay, then f has no local maximum or local minimum at a. Right. So for example, guys, so example, I'm gonna use the same example as as before. So this is example. All right, so we have this example with the f of x, which is 2x cubed minus 2x squared minus 2x plus 1, right? So we try to find where the function is increasing and decreasing again. So in the chart, so just to remind you the chart. So we had this negative infinity, this positive infinity. We had this negative 1/3. This is so this is a negative 1/3, and this is a positive 1. And we said, so this is f of x, and this is f prime of x. So we said there's a 0 here and a 0 here, and we said f prime of x is actually positive on the first interval, then negative on the second interval, and then positive on the third, right? So, and we said that this function is increasing, then decreasing, and then increasing, right? So, so what we are saying now, guys, is that if the derivative change the sign from plus to minus, then your a would be a local maximum. So you see here, for example, here you change the sign from plus to minus at -1/3. So you go from plus to minus at -1/3, then -1/3 would be a local maximum, right? So f prime of x changes the sign from plus to minus at -1/3. So f of x has a local maximum at x equal to -1/3. All right. And again, guys, you can even see it from the chart. You see here it's increasing and then it decreases, right? So this point here would be a local maximum, right? That would be like the highest point in the neighborhood of -1/3, right? So that's a local maximum. This one here is a local maximum, right? It's because the derivative went from plus to minus. Now at 1, the f prime of x changed the sign from minus to plus, right? So f prime of x changes the sign from minus, so from minus to plus at +1, right? So then f of x has a local minimum at +1. At local minimum at x equal to +1, right? This is, and again, you can see just from the chart. So you see here, it's decreasing, and then it's going to increase, right? So then this point, this one here, this point would be a minimum, right? And that corresponds to +1. This is a minimum, right? This is a minimum. Right? So that's why we have, so this function has a local maximum at -1/3 and a local minimum at +1. So, and then of course, if your function, your derivative doesn't change the sign, right? So then your a is not, it's neither a local maximum nor a local minimum, right? So if the derivative doesn't change the sign, so your point or your a is neither a local maximum nor a local minimum. Okay. All right. So before the exercise, we can do. Okay. So yeah, let me first introduce the inflection point, the concavity, and then I will give you an exercise. So this is for the local maximum, local minimum, right? So now what about the concavity of the function? Okay, so this is, so next, so this is definition. Okay, so a function is called concave upward. So f of x is called concave upward. All right. Concave upward. on the interval I if, well, if the derivative is increasing, if f prime of x is increasing. Okay. And so when the derivative is increasing, that's when the second derivative is positive. So when, so this is when the second derivative, f second, is positive. So what do I mean by this concave upward? So okay, so here's an example. So let's say I have the following graph, and I have this function f of x. Okay, so this is, let's say, f of x. All right, so you see, guys, the derivative here, my derivative is, so I'm decreasing, right? So the slope here is negative, right? This is negative, still negative, and now it's gonna vanish, and now the slope is positive, right? So what I'm saying, guys, is that first your derivative is negative, and then it becomes positive. So in this case, actually your f prime of x is increasing, right? Because it's going from negative to positive. Because you see here the slope is negative, and here the slope is positive. So your derivative went from negative to positive. So your derivative is increasing, right? So because the slope went from minus to plus, right? So if I have such a graph, then this f of x is actually concave upward. Okay, so this is what I call, this is what I mean by concave upward. So in this case, it's concave upward. Okay. Now, concave downward. So that will be, so that's when the derivative is decreasing. So this is a definition. So f of x is called, is concave downward, right? If on the interval I, if of course, if the derivative, if f prime of x is decreasing. So this is when the second derivative, so when the function is decreasing, when the derivative is negative. So this is when derivative of f prime, which is the second derivative, is negative. Okay. So what do I mean by concave downward? So here's an example. So let's say I have the following graph, and let's say we have something which looks like, so let's say this is my f of x. All right, this is, so that's my f of x. All right. So first, guys, you see the derivative here is positive because the slope is positive. So here's my slope is positive, but positive, then it vanishes, and then it becomes negative, right? So the slope first is positive, and then it becomes negative. So if you go from positive to negative, it means that your function is or your derivative is actually decreasing, right? So then f prime of x is, f prime of x in this case is decreasing because first we had the positive slope, but then the slope becomes negative, so it's decreasing. So because the slope went from plus to minus. So this is when the function is concave. So in this case, the function is concave downward. Okay. So concave upward, that's when you have like sort of like a parabola which opens up, and concave downward, this is when you have like a parabola which opens down. Okay. So that's what I mean by concave upward and concave downward.
Okay.
Mm-hmm. Right. Now, if you have a graph where you go from concave, let's say upward, to concave downward, then the connection point is actually called the inflection point. So the point where curve changes its direction of concavity is called an inflection point. So let me write down the definition of the inflection point. So that's where you go from like concave upward to concave downward, or concave downward to concave upward. So that's what I call a point of inflection point. So a point where a curve or a graph, where a graph changes its direction of concavity, right, is called inflection point. So this is called inflection point. Okay, so the idea or the example, so I have this graph, and then I have this function, which is first, let's say it's concave upward, right? And then it becomes concave downward, right? So this is here, my function, it's here. So it's concave downward, right? Here it's concave downward, and then it becomes, let's pick a different color, let's say green. Okay, and then it becomes concave upward. So this is concave upward. Okay, so then the connection point, which where you change the direction of the concavity. So let's say this point here. So you see here is this point. So you change the direction of the concavity of your graph. That's what I call inflection point. So this point here, this is what I call inflection point. All right, so you go like from concave downward to concave upward. So the connection between the concave downward and concave upward, that will be your inflection point. Or of course you can go from concave upward to concave downward, right? So yeah, so the point where the curve changes direction of concavity, that's your inflection point, right? So now the question, of course, so when on which intervals the function is concave upward and on which intervals the function is concave downward. So we said when the second derivative is positive, that's where your function is concave upward, and when the second derivative is negative, that's where the function is downward. Now, so when do we have an inflection point? So that's when the second derivative is 0. So so let me write down here theorem. And we're going to have an example just right after the theorem. So the theorem is the following. So I'm going to suppose that the second derivative exists. Suppose f second of x exists. Okay. So if a is an inflection point, okay, then f second of a must be 0. Okay, so the inflection point, so if you have an inflection point at a, then the second derivative must be 0. Okay, but here you have to be careful, guys. So this is a warning. So if you have an inflection point, then the second derivative must be 0 at the inflection point, right? But the warning is that if the second derivative is 0, it doesn't mean that your a has to be an inflection point. So so the warning is that if, so it's possible, you know, it's possible that f second of a is 0, but a is not an inflection point, right? So it's possible that f second of a is 0, but a and a and a is not an inflection point. Okay, so again, the theorem says that if you have an inflection point, it means the second derivative is 0. And what I'm saying is that if the second derivative is 0, it doesn't mean that your a is an inflection point. So for example, let me just first take an example where the second derivative is 0, but your point is not an inflection point. So an example, if you take x fourth, example, let's say f of x is equal to x fourth. Okay, so the graph of x fourth is, you know, it looks like it's like a parabola, right? So the graph of x fourth would be like something like a parabola, right? So so it's just you know, your parabola. So this is just a concave upward, right? This is, you know, concave upward, concave upward. So if you check, so when the second derivative is 0, so what's the second derivative? Well, first, the first derivative, f prime of x, that's 4x cubed. The second derivative would be 12x squared, right? Now, so where does the second derivative vanish? Well, f second of 0 is of course 0, right? That's 12 times 0 squared, it's 0. So f second is 0, f second of 0 is equal to 0, but of course, okay, f of x, x fourth, it doesn't change concavity at 0, right? So this is your f of x, right? And what I'm saying is that, of course, at 0 here, at this point, so f of x doesn't change, so does not change concavity at 0, okay? So again, that's exactly what I said. It's possible that the second derivative is 0 at a, but a it doesn't. But your f of x, it doesn't change concavity at a, right? So your a is not an inflection point, right? Okay, guys. So Okay, so let's do an example and show you how we can get this, you know, the intervals where the function is concave upward, where the function is concave downward, and where the function has inflection points, right? So here's an exercise, for example. Okay, so exercise. So let's say f of x. Okay, let's say f of x equals to let's say well, 2x cubed minus x squared minus 4x plus 1. All right. So the question is to find intervals of concavity. So intervals of concavity. So where the function is concave downward, and where the function is concave downward, upward, and also find the inflection points. Okay. So to find the intervals of concavity, guys, you have to study the sign of the second derivative. So the first step would be to solve the second derivative equal to 0. So we're gonna have, like, you know, as we did for intervals of increasing and decreasing, we had to solve f prime of x equal to 0. Now for this intervals of concavity, so step 1 would be to solve the second derivative is equal to 0. So step 1 here, step 1 would be to solve the second derivative equal to 0, and the step 2 would be the chart of the sign of f second. All right. So for first step, so step 1. So I have 5 minutes to finish this example. This is not exercise. This is an example. Right? This is an example. This is an example. So and then I guess next time I will continue with more examples, right? So step 1, I have to compute the f second. I have to solve f second of x equal to 0. First, I compute f prime. So that'll be 6x. 6x squared minus 2x minus 4, right? And then that's f prime. F second, that's 12x minus 2. So I have to solve, Sorry, I think I moved to the next page. Sorry, guys. All right, so here's my f second. Okay, so I'm gonna probably just, all right, so then we have to solve. I'm gonna probably zoom out. Okay, so I have to solve f second of x equal to 0. So that's 12x minus 2 equal to 0. So plus 2 both sides. So that's 12x equals to 2. Divide by 12. Here's over 12 over 12. So then my x is equal to 2 over 12, and that will be 1 over 6, right? So I got one solution. So again, guys, I have to solve, this is a solution of f second of x equal to 0, right? So now I got this 1 over 6. Now I have my chart. So step 2, the chart. Now we're going to do the chart for f second. So for f second of x. Second of x, right? Oh, come on. All right, I don't know what's the problem with the Zoom or whatever. Sorry. So this is so we had f second of x. We said it's 12x minus 2, and we had to solve equal to 0. So then we got x equal to 1 over 6, right? The solution of f second of x equal to 0. Now the step 2, we have this. So we have to make this a chart. For f second of x. So again, we have this number line, negative infinity, positive infinity. So I'm going to put the solution of f second equal to 0. That's 1 over 6. So here's my 1 over 6, right? And then we have a first row. That will be my f of x. And the second row, that's my f second. So f second, it's, or second derivative of f is 12x minus 2, right? Now I have this line coming from 1 over 6. And here I have 0. I have 2 intervals. So from negative infinity to 1 over 6. And the second interval going from 1 over 6 to positive infinity, right? So as usual, you pick a number in the first interval. Let's say you pick 0. You plug 0 here in the second derivative. That will be 12 times 0 minus 2. That will be negative 2. So the sign on the first sign of the second derivative, it's negative from negative infinity to 1 over 6. Now I'm going to pick a number on the second interval from 1 over 6 to positive infinity. So let's say we pick 1. You plug 1 in the second derivative. That's 12 times 1 minus 2. That's 10. That's positive 10. Right, so we have positive 10 here. Right, so then we said, guys, if the second derivative is positive, then the function is concave upward, right? So then the function is going to be concave. So first, it's the second derivative is negative, right? So it's concave downward. So it's concave downward, right? And then on the second interval where the second derivative is positive, so when the second derivative is positive, your function is concave upward, right? So it's concave upward. Okay. So then, to answer the question, of course, here the 1 over 6 is going to be an inflection point because your function f changes the direction of concavity at 1 over 6, right? So here it's concave downward, and then it becomes concave upward after 1 over 6. So to answer the question, so f of x concave downward on negative infinity 1 over 6, and f of x is concave upward on 1 over 6 positive infinity. And finally, x equal to 1 over 6 is an inflection point because your f of x changes direction of concavity at 1 over 6, right? It goes from downward concave downward to concave upward. So it's an inflection point. Right. Anyway, guys, I guess I'm gonna stop here. So next time we have probably 1 or 2 exercises about this, about this shape of the graphs. And then I guess I will move to the chapter 4. All right. So yeah, so I'm gonna stop here, guys. So thank you, everyone. Thank you, and I wish you happy Thanksgiving. Right? So enjoy your holidays, guys. Enjoy your Thanksgiving.
You too, Professor. Thank you.
Thank you so much.
Thank you, Professor.
Take
Have
care.
a great Thanksgiving.
You
I'll
too.
see you Monday.
See you Monday. Take care. Thank you, everyone.
Bye-bye.
Bye-bye. Thank you.
We don't have class on Wednesday.
No, because on Wednesday they'll follow a Friday schedule. So if you have classes on Friday, then you're gonna have them on Wednesday.
Oh, okay.
So this Wednesday follows a Friday schedule. Yes. So next time we're gonna meet is next Monday. All right.
Okay. All right. Thank you.
Thank you. Thank you, Ibrahima. Take care.
Have a good night.
Good night. Thank you.
All right.
Good night, everyone.